All right. So in inferential statistics, we will see a little bit of basic recap of what we have already learned. Conditional probability, some probability distributions, probability mass function, density function, normal distribution, okay, standard deviation, and some concepts of z scores. And then we'll straight away go ahead with inferential statistics. Now, in uh, we are just reading the data here, okay, and in probability again, I'm making use of a library called dabble, okay, data analysis library. So you have given the link here for dabble, so you can just go ahead and read it, but this is only for your understanding only, it is not meant for production use. Okay, so you can go ahead and run some, generate some scores for your understanding. Okay, so that's I wanted to call out clearly. So I will give the link here. So just do a pip install dabble. You will get the dabble library. Just refresh the kernel, and from this dabble, I'm going to use dabble only for mainly for plotting purposes. Okay. Here I'm reading the data. I'm just checking how many rows and columns are there. 81 columns, 1460 rows. Head will give me the first 5 columns by default, or if you specify whatever the value here, so many rows of data will be printed. Likewise, data.tail will give me, tail will give me the last end 5 rows, um, or whatever the value you specify, it will generate that. Here I've imported the dabble library. The reason why I'm using dabble is because I don't have to manually generate the plots at column level. Instead, I provide the whole data. I specify what is my target variable going to be. Then it will start comparing all my data against that um, sale price target column. Okay, so you have automatic plots for classification and regression. That's why I'm using. I don't want to manually generate and spend time on it. That's why I'm generating automatically. The moment I run that, I'll get the histogram of what my data distribution looks like. Immediately I can say this is left skewed or positively skewed, and we already calculated the value in previous class. 1.88 is the value. That means there is a 80% more deviation, more skewness. Okay. um, okay, so it starts comparing sale price against all other features. Now here is you, as you can see, on the y axis you have sale price, and on the x axis you have overall quality of the house maintained. Okay, so central air, if you notice, wherever the air supplication is more, such properties have fetched more value. Okay, so as you can see, it keeps on increasing. Okay, so overall quality is calculated on a scale of 0 to 10. Wherever the house was rated as 10, actually wherever the house was rated as 9, that has fetched a more price. Okay, maybe this has some human bias involved in decision making. Okay, we see 90% and above as sometimes we see 90% and above as more merit students, right? And we bucket them into same category. If a person scores 98, 99 or whatever, and 100 means sometimes we take it lightly. And that's some sort of human bias. Okay, so don't worry about it. But as you can see from the data, 8 and 9 have fetched more higher prices. Likewise, ground living area, this we already saw. Wherever there was less central air, okay, the data is split here, but if you keep aside the splitting part, and generally if you see, higher the ground living area, higher the sale price. That is one. Second thing is, now if you compare the, take into account the splitting on account of central air, as you can see, higher the air supplication was, more the prices. So lower red values have fetched lesser price, even if the ground living area was high. Okay, so 2000 square feet or 2500 square feet area has fetched lesser price with central air conditioning. Okay, or maybe central air uh, availability. Maybe you can take it as actually it is air conditioning only. Central air stands for central air conditioning, and in US it so happens thus happens that the temperatures are extreme. When it's negative, the entire house will become um, very cold. So that's why they make use of heat pumps and central air conditioning, whatever. So wherever the central air conditioning was used, the house prices were quite high. Okay, so generally people have purchased the properties from somewhere ranging from 850 square feet to 2000 square feet, high concentration here, and paid more price just because of central air conditioning. Okay, so that you have to understand. Likewise here also, as you can see, year built, which year the house was built. So very less houses that were that had very old have fetched the, I mean, that were built on a very long back. So they have fetched high price. But generally speaking, this follows a trend. Okay, so this sort of trend where properties built after 2000 have fetched higher prices, and somewhere between 1960 to 1980 also have fetched a good amount of density. You can see here they have been sold a lot, but the higher prices are somewhere here. So this zone, and all these houses have centralized air conditioning availability. Okay, likewise garage area, we already saw garage areas with only one single garage where only you can park maybe one car has fetched very less prices, as you can see here. That is 200 to 300 square foot of area has fetched very less prices. No, you can see no is zero, which you can see here. Very low garage areas also sometimes they have fetched decent amount of pricing here, as you can see somewhere 200K. Okay, 2 lakh dollars or $200,000 they have fetched here. And as you can see, generally if you had houses with two and more, okay, three generally have fetched higher prices here. So if you want to calculate the uh, if you put a limit of 300K, lower limit as 300K, and write a condition to fetch the houses which has been sold and their number, then you can see the prices have gone up basically. So more houses have been sold. So this way you can see different variations of with each plot. You can see how the sale price has differed with each feature. So here total basement. Okay, total basement value is calculated in square foot. Okay, SF is square foot total basement. So you can see whichever had the centralized air conditioning along with higher the total basement, more is the price. So there is a positive correlation. If you see the line is going like this, if you plot a line, okay, so here it is going like this. Here also there is a positive correlation, positive correlation, positive correlation. Okay, so
Uh,
yeah,
uh, can I ask a question
yeah,
here?
yeah, please,
Yeah, yeah. The thing what we see here is in each of these we call this as a scatter plots, right?
yeah,
And here sell price is on the y-axis for each of this, that
mm-hmm,
being the target variable,
mm-hmm,
and in each of these scatter plots, one feature is selected like overall quality,
yeah,
living area, or
yeah,
year of build.
mm-hmm,
And then there is this is the plot which is by default automatically it has considered the central air
yeah,
conditioning.
yeah,
Yes or no for the first three plots,
yeah.
whereas for the fourth plot
It
it
is
has by
garage.
default selected the garage cars.
Yeah,
I mean, or
it
the
is
next
automated.
line if it's
Okay, the library is
okay.
automated. But if you want to
So,
manually do the same thing, you can do by
mhm.
running this code. Okay, it's called SNS dot
Heat
scatter
plan.
plot. SNS
Okay.
dot scatter plot, and then you can add x y values, and then there is something called hue. Okay, so if you
Okay.
pass this hue value, okay, hue order, hue norm. So hue value. So what this hue does is it distinguish. This is exactly what the hue is. I mean that whatever is shown there. Okay,
Okay. U stands for.
it starts. No, hue is just hue only. You can check the meaning of hue. So
Okay.
it's,
It is that parameter.
yeah, it is that parameter that distinguishes between what basis on what to decide how to bifurcate. Here it is central
Like
air
here, the
conditioning
central air is the hue.
hue. Here it
Okay.
is central air
Okay.
is the hue. Here garage air is the hue. Okay, that way. So basis on these factors, Dabble has automatically selected. Okay, but for us, if you
Okay.
want to manually check, we can pass the hue value. Okay, so here,
So basically, X value, Y value, and hue value.
yeah,
Correct.
x value, y value, and hue value, that you can just verify also if you want. Data dot, what was that, ground area. Okay, and then data dot sale price, and then hue value I can pass as, uh, hue values data dot central layer is what is selected. Okay, pass it as a string instead. Scatter plot takes 0 to 1 positional arguments but 2 positional. Okay, fine, fine. Yeah. Okay, it could not interpret. For garage area, it could not interpret this. Maybe for garage, it will interpret only garage. Okay, so that's why
That's
for
fine.
garage area, this is taken as the garage
So
car
we can
system.
take it as sell price, and overall quality. The same kind of plot if we try to
Okay,
get.
overall quality. Yeah. Okay, so here you can run it as, uh,
Central layer.
yeah, central layer. Spelling is correct, right? Central layer. Okay.
Or we can have data dot
Yeah.
central layer.
Okay. So ideally you can pass it as string also. Anyway, so this is what it
Mhm.
looks like. This is what that plot is. Okay. Here, but you can see, a swarm of plots. Okay, swarm of values. Maybe it's called. Hmm. Okay, this is a different representation, but some value they have tweaked in order to get this density. Maybe density is modified, but otherwise,
Mhm.
it looks like this only. Okay, some density is
Okay.
modified,
Yes.
but yeah.
Yeah, yeah, no worries, no
So
worries.
this is how
It's
you get this
similar.
hue.
It is similar. Yes. I
Okay,
think they have bucketed it here. Like,
no, no, they have not bucketed. I mean, this you get by passing density value somewhere in the parameters. Okay, size is
okay.
none. Maybe size. What does size? Grouping variable will produce the points where different sizes can be categorical or numerical. Yeah, maybe they have done something to size, or they have used some keyword
Categorical
argument.
value.
Yeah, yeah.
Yeah, they have
Somewhere they have,
converted into category.
yeah, yeah. Somewhere they have done that. That's why they are getting
Okay, no
that.
worries, no worries, no
Anyway,
worries. That's fine. Got
that's
it.
not the
Yes.
concern. So here, this is how you can generate the plots for whatever you see. You can generate the hue here, as you can see. Okay, you can bifurcate. So that is what the library has automatically done, but selected the best possible hue values. So likewise, you can see the sale price variation. Here's in a very instant you can see positive correlation, positive, 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 although very less positive but still positive. Here also positive, positive. Here also positive, and here it is highly scattered. Open Porsche SF, although you can see it goes like this only, but still it is little bit scattered. There is a very no definite way to say how much of positive correlation exists unless we calculate it. Okay, So this way, this is one thing that Dabble does. Second thing is, it also tries to calculate the outliers. Okay, at each value, it has taken the value, as you can see. At each value, what is the box plot? How many repetition of those values exist? Against that, it has calculated. Although I don't prefer this particular x value, I would have done it in a different way, because this does not make sense. If you see the y-axis, it absolutely does not make sense. But anyway, so you can do it in your own way using sns.boxplot. So box plot will tell you, like we saw in the previous class, it tells you the IQR range. It tells you this line that you see, the bottommost line, this thing of the box. The leftmost side of the box will give you 25th percentile, centermost line will give you the median, and the rightmost line will give you the 75th percentile.
70.
Okay, and this will give you the max value, this will give you the minimum value, and whatever the range, whatever the exceeding to these value will be outliers. Okay, so all these are actually, this is not max value, this is 100 percentile. Okay, and anything above that is outlier, and the highest point here would be the actual max value in the feature value. Okay, so this will plot the various outliers for us. Immediately you can see which feature has outliers, and which we also do something called outlier treatment. Okay, that we will see in the data analysis. Outlier treatment, we do either by calculation of z-score after transforming these features into normal distributions, or we calculate the outliers basis on the IQR, or there are other ways or also for handling this outliers, something like capping. Okay, capping is another technique to handle outliers. So many such things are done. Okay, that we can immediately understand which features need outlier treatment by looking at these plots. Now just giving a
Sorry to interrupt you,
yeah.
but I'm not clear with the idea of hue. What does hue represent?
Okay, hue is, let's just say, I will remove this hue, maybe then you can understand. Okay, so our general scatter plot looks like this. Okay,
Okay.
so we have plotted overall quality of the house versus sale price. This is what we can say. From this graph we can infer, higher the quality, higher the sale price. As you can see, the plot has gone like this, prices have gone in an increasing manner. Now I want to also know that how many of these houses had air conditioning. Okay, I just want to divide in the same plot only. I want to divide the data basis on a condition. The condition is how many of the houses had a air condition. Or another example, let's just say I plot your salaries of various IT employees and various companies or various roles I plot, and basis on the role I assign some numbers to those roles, and then we calculate the salary. Then we'll get very similar plot only. So mainly the doctors coming here falling in this bucket, doctors earning higher, doctors, surgeons, and all of those. Next comes the um, again not only doctors, surgeons, but also CFOs, CIOs, CEOs, COOs. So all those jobs will be here. Next will be the high paying job, white collar job, mainly like your software engineers, maybe your high level senior project managers, directors. So all these will fall in this bucket. But now I want to know how many of those are males and females. Okay, then for the same data we have something called a hue. Okay, what is the meaning of hue? You can check, look it up. Hue meaning, okay, hue meaning, it stands for color. Okay, variations of colors. But in statistics, so you can see hue is just a parameter that adds extra distinction, extra dimension. Okay, to your, mainly your categorical data or numerical data, whatever it is, it just adds additional differentiation. So if I want to know how many of these houses also had air conditioning, then I will generate a hue value. Now I can immediately see how many of those did not have. So all these red points did not have central air conditioning, hence they sold for lesser prices. That is the inference here. And wherever the houses had central air conditioning, they sold for higher prices with overall good quality, basically. Likewise, for salary example, you can pass the hue as gender. Okay, and maybe here you had occupation, here you had salaries, here you had gender. That will also give you a very similar plot. Okay, maybe the distribution of females would be higher, but anyway you will get very similar looking plot. Okay, that is what hue is. Hue is just a adding extra dimension. Okay, is that clear?
Yeah, yeah.
Okay, next let's look at basic probability very quickly. We will see. So probability is nothing but the chance of occurrence of event, that is likelihood of occurrence of an event is what probability talks about. In the probability we talked about experiment, which means you just repeat this experiment is nothing but the entire trial, basically. Tossing, for example, tossing a coin is an experiment. Okay, outcome is the end result of that trial. An event is nothing but just the trial itself. Event is any event. It's basically a form of experiment. Okay, so and rules also we saw. Okay, these rules, we saw that for any event the highest probability would be 1. Okay, and the probability for event that occurs certainly is also 1. Okay, for example, thunder and lightning example. Whenever it rains, maybe the lightning occurs for sure. Sometimes we see it, sometimes we don't see it, but nevertheless lightning occurs. Only if lightning occurs, rain will occur. I'm not sure if you know that concept. If you read up how rainfall happens, so you will get to know that there is a role played by static electricity, which means there is a transfer of electricity generated during that period transforms to lightning, and the rainfall happens. So that such probabilities will be a 1. Okay, and the probability that an event will not occur surely for sure is 0. If today if you look at sunlight, so the color turning to some other color, sunlight yellow, sunlight becoming green is 0 probability, it may not occur. Okay, and the probability of the complement of a event 1 is taken as 1 minus whatever the probability of the event. This also we saw. Okay, and mutually exclusive events are those events that can never occur simultaneously. You can't pass and fail the exam simultaneously. That simply cannot happen. So hence we say, um, for such events, okay, where there is a mutual exclusivity, you can define the probability of occurrence of uh, events by different means. Okay, so for such events we apply, such events, if you want to calculate the probability, you can apply the formula here. Okay, so for any two events A and B, okay, the probability, at least if you want to calculate at least what is the probability if one of them occurs. Okay, so that if you want to calculate, then you need to know what is the probability that both of them can occur. Okay, so likewise you can calculate what is the probability that neither can occur, or whatever the common factor is between them, and likewise you can substitute in this formula to get it. So one example is given. So 3% of the people, American people, have breathing issues while they sleep, and 10% of the Americans have leg syndrome. So does that mean 13% of them have one or more? No, because there is some common factor. Some of them might have both. Okay, so that factor we have to take into account. P of A intersection B we have to take into account, and accordingly calculate. Okay, accordingly calculate P union A union B. Okay, so that you have to remember, because they are not mutually exclusive.
Probability is always measured as 1 or 0.
It is always between 0 and 1. It is always between 0 and 1. There cannot be negative probability. Okay, either the probability will be 0, or it would be between that value 0 and 1. Okay, all right, so we are taking we are just elaborating this concept to one of our examples. let's just say we want to calculate a probability of someone picking a house in a neighborhood of old town or a new town. So so for that we have a feature called neighborhood, and if we check the neighborhoods, we have different neighborhoods, right? So like as for us we have nagars and we have puras and whatever other areas we have, right? For like Gandhi Nagar, some Nagar, Shivaji Nagar, etc. So there they have, in Boston they have these type of areas like Crawford, okay, Berkside, so something like that, okay, Sire, whatever. Old Town is one of them. So what is the probability of someone choosing the house in Old Town versus all others is what we are trying to calculate. So for that, in order to calculate, we know we are applying a condition. We are choosing a condition that if the neighborhood equals to Old Town, fetch all the data. This is how you understand this. First, read the condition inside. Read condition says fetch all the values in the neighborhood that belong to old town, and fetch all of that data, and choose the first row value only. Okay, that is what it is here. So if you want to understand this, if you notice, first notice what data of neighborhood is. Okay, it is what these values are, and out of that I'm applying, okay, this old town. Now I got false and true values. For certain, wherever it is true, I'm saying fetch that values. Okay, now it will start fetching me the values like this. Okay, and out of this, if I want, I can even apply only data neighborhood. This is how you apply. Out of this, if you want only data of neighborhood, you can get only data of neighborhood. Something wrong. Yeah, that's because of we haven't chosen the data yet. One, two. I didn't use the end bracket. That's why. One, two, one, two. Okay, one, two, one. Why is it incomplete input? Okay, hold on. Data dot neighborhood equals. Yeah, I mean that. Okay, let's try this. Okay, you are getting this. Out of this, you want to choose. Let's just say land contour. Yeah, you get the land contour. Okay, maybe I pass something else. Anyway, so if you want only neighborhood, you'll get only neighborhood here. Okay, so likewise you got all the old town values wherever the values. Notice the rows where the old town was available. Notice the rows now. So out of all these values, okay, it has chosen the neighborhood wherever the neighborhood is. Likewise, I'm choosing shape. If I give shape, it will tell me how many rows are there, how many columns are there. Out of that, I'm choosing only rows, 113. So this entire thing will give 113. So what this thing is calculating is 113 are the number of houses in the old town. First we are calculating the number of houses in the old town, and out of that we are dividing it by all the houses. Now all the houses you can get the same way. For total 100 1460 rows are there, so that we are dividing and calculating the percentage. So the probability of someone picking the house in old town is 7.74%. Straightforward. Is this understood? Okay, how to fetch the values.
Yes,
Okay,
yes.
now we are also talking about conditional probability. Let's just say there are 10 candies in a bag, 5 green and 5 blue, and if you want to calculate what is the probability of you picking 3 blue, then it is, well, first you have to calculate what is the probability of picking green, which is 5 by 10 total, and 5 by 10 is again for blue. Okay, and because there are 5 green and 5 blue, again you have to multiply. So how are they doing it? So if you pick one candy, for the first candy, so what is the question? The question is probability of getting 3 blue candies. For the first candy, the probability is always 1 by 9. Okay, sorry, 1 by 10, because there are 10 candies. Out of that you are picking one. Okay, it could be blue, it could be green. it could be anything, right? So that's why it would be, so for first way it is half. Okay, let me calculate 1 second maybe. So let's just say you have green, 5 greens, 5 blues. Okay, even before this, if I want to calculate what is the probability of fetching one candy out of 10 blue candies, this is straightforward, right? You're fetching 1 divided by 10. Very straightforward, no doubt here. 0.1. Okay, the probability is 10% or 0.1. But if you had
Are you
5,
sharing some different screen? Because I can see only the screen like where the code is written.
where the,
Code is written. If you're writing something, I cannot see that.
no, I'm typing here, no?
Okay, okay.
I mean, I'm typing here. This is the one, same screen I have. Okay. Anyway, um, so if you have 5 G's and 5 B's, okay, irrespective of what you have. So earlier in the first case, the probability of choosing one B out of 10 B's was 1 by 10. But so if you're calculating the probability of picking one blue candy, okay, and the question is getting 3 blue candies. So one, 1B, one B and 1B you have to get 3 times repeatedly. Okay. So we have already seen this in head and tails, or even in dice example. What is the probability of you getting, so h of t, we already have seen, right? So for rolls, so the probability there was, you take one side, okay, divided by, if you rolled it for 5 times and because it had 6, then you would calculate the probability something like this. So okay, 1 divided by 7776 different ways there were, and out of that you would get one probability. Okay. And the probability of you getting a certain side, let's just say one side 5 times, 1 1 1 1 1, right? So this probability also we have calculated somewhere, if I remember, if I recall correctly, 0.00128, something like that, whatever the number was. This is how we calculated. Same example here, there are two different conditions only, so this will become two different ways. Okay, two different possibilities. And how many times you are going to repeat? 3. Okay. So if you do this math, let's do that math. 0.125. But because you're, okay, this would have been for, there is a little confusion here how they are calculating the probability. Okay, let me see. Okay, the probability of taking the blue candy repeatedly is what is being calculated. So if you take out one candy first time, the difference is, if you take out first candy one time, then there are 9 left, and out of 9 again you are taking one. Okay, then there are 8 left, and out of that also again, first time when you took the candy, okay, if you take the candy out for the first time, then this would become one less B. Total there are 9, but there are 4 candies only out of blue. Now out of blue candies are 4 only. So here the second time the probability would be 4 by 9. First time the probability would be 5 by 10. Okay, this would be 5 by 10 because there are 5 candies. Okay, second time it would be 4 by 9. Third time would be 3 by 8. Here the conditions are different because there are two different sets of candies here, and you're getting subtracted each time you're losing one candy, right? That's why. Otherwise the general probability would look something like this. If you had,
Yeah. So the
if you are
upper one,
not, Mhm.
so the upper one is without replacement, and the lower one is with
is with,
replacement. I mean, select it and put it back,
yeah,
right?
yeah, this is without replacement. Okay. um,
The upper one is with replacement.
with
No, this
replacement.
is with replacement. No, no, ulta or opposite. The bottom one is with replacement. You choose it and you put it back in the sample. So that is
Okay.
with replacement.
Okay,
Yeah,
fine.
and the upper one is without. We are not replacing it. We are just keeping it aside, right?
Okay. Yeah, would be, yeah. Okay, it's fine. Yeah, that is what. So if you're losing one candy each time, okay, you will have to subtract one value at each time. And now if you want to calculate what is the probability that you will get blue all the time, so this you have to multiply all these three values, then whatever you will get 0.0833, that is 8.3% of the chance that you will get blue all the time. Okay. And this we had done using from random module np.random. We had chosen choice, and out of that choice we had generated. If you can repeat the same thing by looking at old example, you'll get this value easily. But because the question is little different here, so you're, if each time you take the candy you will lose one candy, right, in the
So
background.
I have one question. Like with replacement means, like every time you are picking up one candy, you are adding one candy to it from this in the sample.
Yeah.
So like if I am taking one blue candy,
Mm-hmm.
then we are adding one blue candy again.
Yeah. The other way it would be like select, pick one candy, note it is a blue candy, and put it back in the sample,
Uh,
right?
okay, so you are taking one candy, blue candy, then again putting it back in the sample.
Yes. So
Yeah.
again, we are getting the same sample size will be
Okay,
10 only every
okay,
time.
okay,
Every
got
time
it,
it
got
will
it.
be 10. Without
Okay,
replacement means we are taking it out and keeping it aside, not in the sample space
okay,
again.
okay, got it.
Okay.
Am I right? Sorry.
Yeah, yeah, fine. Yeah, yeah, you're right. So if you multiply all these three, you will get this 0.0833. And if you want to repeat this experiment with replacement also, we already have done that in the previous class. Probability, you can just change the values of h and t with g and b, and you can repeat it. So you'll get the same values. You can same way you can get the probabilities. Okay, now we want to apply the same concept for old houses. So we want to calculate, okay, picking a old house town. Okay. And again pick the same house. What is the probability that the customer will pick from the same neighborhood for the second time? Okay, that is old town. So that you can calculate by this same concept. Okay. So if you pick the first time, okay, let's just say again they have explained the same thing. So if you pick it the first time, the probability was, which we already calculated, there was 7.74% chance. Second time what you will do is you'll subtract one value from old town. Okay, because you have already selected one house, and then again you will, that's why this value is subtracted by 1. And from all houses also you'll subtract by 1. Why? Because out of all houses one house is already taken. Now if you calculate the probability is 0.59. Okay, the probability of person picking the house from the same neighborhood is 0.59 with this formula. Okay.
Are we subtracting their minus point 0.1 from all houses? Or wait, oh
Here
yeah,
we have
in the
subtracting from both old house.
one, and this is minus point 0.1. All houses minus point 0.1. It seems, is it?
No, no, from all houses also we are subtracting minus 1,
No, it is. Okay,
not point
maybe.
1.
Okay, okay. Yeah, yeah, yeah. It's not point 0.1. It is 1. Sorry, there
It
was
is.
something in my screen.
Oh,
Fine, fine.
okay.
Thanks, thanks.
Okay,
Sorry.
do you want me to increase maybe?
No, no, it's okay. It's okay. It's okay. I
Okay.
mean, there was something on my screen. That's why I misinterpreted it. Thanks.
Okay, no worries. Okay, so again for dice example they have shown the distribution, if you roll it two times, what is the probability you can get 191? So it is 1 by 36. Likewise, you can, what is the probability you get 1 comma 2 or 2 comma 1? So that way they have calculated for all sides. Okay. uh, while this being the sum of the sides. Okay, each time when you roll, what is the probability that you will get 1 and 1, and the sum totaling to 2, that is the probability of 1 by 36. That way the highest sum that you can get is, I mean, the most number of times you will get the sum is 7, and the highest sum is 12. Okay, 6 and 6 if you roll the uh, if you roll it twice. Okay, anyway, so this is how you can calculate the distribution. Taking this concept further, we also discussed PDF and PMF, which means the area at any given point for a discrete random variable or discrete distribution is called as probability mass function. For continuous values, which are your decimal values, it is called as probability mass function. At the end of the day, both are same only. It's just that the underlying values, type of values, are discrete. Discrete means exact values, non-decimal values. Those are, those, for those values we call it probability mass function. Okay, and whatever the for same thing for continuous values, we call it as probability density function. Okay, this also we saw, and normal distribution also we saw. Generally skewness, if you have this type of graph, this is showing as skewness, but the same plot if you is center, at the center, okay, so that is, we call it as normally distributed. Okay, and when the plot is normally distributed, this also we saw above, that 95% of the data lies within first two standard deviation. 99.8% of the data lies within range of 3 standard deviation. Okay, here they have taken the example of students height. Okay, if 95% of the students at school are between 1.1 and 1.7 meter tall, assuming the data are normally distributed, okay, you can calculate the mean. What is the mean? Basically, mean is at the center, we know. You have to picturize this normal graph. You just add those and divide, so mean would be 1.4 meters. Likewise, if they shade this first region or the last region and say what is the percentage of the people lying in that distribution, because you already know, you have calculated, it is 2.14 or 2.15%. Okay, so you can straight away you can select the answer. So that way, or if you want to calculate this region only, you can do the mathematics. You can if they give, if they want you to calculate this, they will definitely provide some other values by means of which you can calculate. So accordingly you have to remember and calculate. This is I believe this is 68%, this is 95%, and the rest is 99%. Okay, 3 standard deviation. Likewise, we have seen sample mean and population mean. It is next to impossible to calculate population mean, simply because you can't get the data for population. Hence we take sample mean. Okay, sample mean is, we are considering only
I
500
have.
users. Mhm.
Can I ask one question here,
Yeah, yeah,
Sun?
please.
When we talk about the Z score here,
Mhm.
so the Z score is the sigma value in which a particular point lies, right? They are saying it is 1.85 meter tall. So he is lying on the right side, that is 3 value, 3 sigma value.
Yeah,
So it is G score is that sigma value where that particular point lies. So if we consider a student who is having 1.4 meter, the mean is here 1.4.
yeah,
So the student who is having the height of 1.8 meter, 85-meter
zero
height,
standard
his
deviation.
height is, so it will be in the 3. So its G score is 3. Whereas if we consider a student who is barely 1.2 meter high,
Mhm.
1.2 meter height. Okay.
Mhm.
Now in that case, the Z score will it be -2
Yeah,
if the
yeah,
height of the
yeah,
student
you are
is
right.
1.2?
Yeah,
The
yeah,
Z score. So Z score is that sigma coefficient of sigma in which region that particular data point lies. So will it be minus? So the Z score can have the values, discrete
from
values like -3, -2,
minus 3.
-1,
Yeah, yeah,
and
minus
one,
3
2,
to
3.
plus 3, it can have values. Actually it can have
Discrete
even
values.
values even beyond that. Okay.
Okay, that is for 99 point. So if the data point is lying outside
Yes.
this
Yeah.
99.15.
Yes,
range, right?
yes, yes. Yeah,
Okay, okay. Thanks for
yeah.
clearing.
Okay, so now because we only talk about sample mean and sorry, we deal with metrics on samples and not on the population. We have to understand certain things. Okay, how does the sample impact the population mean? I mean, how is this sample mean helpful for us? Is it closer to the population mean? So all those things we will calculate in the inferential statistics. Again, there is central limit theorem. I think we studied this, but we will repeat this here again. Okay, what central limit theorem states is, irrespective of whatever distribution you have, doesn't matter what distribution you have. Okay, if you start adding more and more data points, okay, initially if you see n value was 1. Okay, n is nothing but here. N is the value, some random values taken. N is some random values taken, and when you have this n value as one, only one random value you have taken. Basically, understand like that. Only one array of data you have taken. Okay, so if you take some random values, let's just say some 1,000 random values, or in this case, okay, they have specified n equals to 1. That means the entire array they have taken once. So whatever the value is, doesn't matter. This is generally how the data would look like. Okay, this in other words is also a variation of uniform distribution. Okay, flat, what they have represented is more or less like uniform distribution. And exponential distribution we already know. Okay, the distributions, if you want to recall, they look something like this. Okay. So if you want to recall, um, types of distributions we will see. Okay, no. Okay, yeah, this one. So if you notice, the distributions will look something like this. This is what uniform looks like. This is binomial, this is Bernoulli. Okay, Poisson. Exponential looks like this. Okay, it is at the peak initially, then it goes down, right? So that is what we see here. Okay, and likewise you see the beta distribution. Slowly, first initially it will be low and then it will increase. Okay, but the point I'm trying to make here is, you have taken this random values, certain values, doesn't matter what values, and you have if you're going to repeat the same values multiple times, okay, you're increasing the values. If you go till 200, now see, there is not much difference in the distribution after increasing the values multiple times, right? So essentially what we are trying to say is, if so central this is what central limit theorem says, the variance or the mean of the distribution will come close to approximately equal to the mean of the population. Okay, mean of the sample, or the, okay, initially mainly the mean of the sample will resemble the mean of the population if you increase the sample size. Okay, that is what central limit theorem is saying. Doesn't matter what the type of distribution initially you had, if you keep on adding more and more and more and more data sets. Okay, let's just say you calculated the area sorry, you calculated the scores of students from one school, and they will show one particular distribution. But if you start calculating the scores of the students of the state level, country level, entire continent level, they will start resembling the means of the population. Okay, they will start resembling the mean of the population. The mean of the sample will become the mean of the population, or approximately equal when you increase the sample size. That is what the central limit theorem says. So to show that central limit theorem, they have taken some random values. Okay, they have taken some random or random distribution. They have taken exponential, they have taken beta. You can even take uniform or other Poisson distribution, Bernoulli, not Bernoulli because Bernoulli has only one trial, binomial. Okay, whatever the distribution you take, doesn't matter. If you keep on increasing the number of repetition of those values, lin space will create the equally spaced values. So don't worry about it, I will teach this in data analysis. But what they are doing is they are just plotting the mean of these all these values. If you increase, then your distributions will become like this, centralized, with centralized mean. Whatever the highest bar is, will that will indicate the mean value. So that's what central limit theorem is. Okay, very important concept. Next thing is confidence interval. Very very important, I tell you, because for inferring your end results of the model, predicted values, so you need confidence in interval. So no one will accept, when you do a model prediction, model inference, your stakeholders will ask you what is your confidence on this. Okay, how confident are you that your model has predicted the correct answers? That is what confidence interval will tell you. Basically, confidence interval is just a estimate that we compute, that will tell you that whatever the parameter that you are calculating, that is in proposed range. If you say, for example, I have 90%, 95% confidence interval, then what you are essentially saying is 95% certainty that this value is within the range of population mean value. Okay, or 95%. Okay, okay, let me show you and explain. Okay, here what we mean is this red line indicates the mean. Okay, mean is 1 lakh, let's just say 82,000 is the mean of the sale price of the houses. At this point we are calculating the confidence interval. Okay, if I say 95% confidence interval, what I'm essentially saying is my point, data point, that has been plotted, selected by the model, is lying within 3 standard deviation or 2 standard deviation or 95% of these values. Okay, so it could be here, it could be here, it could be here, wherever, but this entire line will indicate 2 standard deviation value or 95% range of the values. Okay, are you following? So in this case also it is here, but nevertheless it is still close by to the mean. And how much close by, that will give you the, confidence interval. How much closer it is, how much within what range it is closer to the mean, is what your confidence interval tells you. Okay, a confidence interval of 95% would mean that if we take some certain samples, then 95% of our samples will will be closer to, or will contain population mean. Okay, population mean basically. Did you understand this concept, confidence interval? Here from this plot, okay, from this plot, this is your mean. Actual mean is 4.257. Let's just say I have a point here where my pointer is. Let's just say my pointer is there. My point is, my model is predicting the end result is there. Now what it means is the distance from this to this is whatever the distance is. What I'm essentially saying is my point lies within 2 standard deviation. If I'm to say 95% confidence interval, I'm saying within 2 standard deviation my point lies. Okay, if I say 99.7, okay, that means I'm mainly depicting the range. Okay, so that way you have to understand, basically my point is very closer to the actual mean of the um, data set. Okay, so much confidence
Okay.
interval.
Okay. So can I ask you one
Yeah, yeah,
thing about the confidence? So let us, can we go to the graph there
yeah,
for the
yeah.
confidence interval? Yeah. So let us say the model is making some prediction
Mhm.
and it is close to the mean,
Hmm.
meaning that it is in the plus sigma and minus sigma, meaning
Yeah,
that it is lying in 68%, 65 or 68% of this.
yeah.
So is it better to have the narrow range or is it better to have the wide range? Because if we are providing the wide range, say for example, we are considering plus
Hmm.
minus 3 sigma, that is total 6 sigma.
Yeah.
So there, or anyhow, that point is going to lie in that particular 99.15%. So
Hmm.
is it better to have the confidence interval range as a broader one or the narrower one? I think, as per my, I mean, let us put this as a question to
Hmm.
everyone who is, trying to understand this concept. That is it
Yeah.
better to have a narrower interval of our confidence, or is it better to have the broader range? So according to me, if it is the narrower range, so it will be close to the mean
Closer to the
and
mean.
giving us the higher probability. This is what I feel. I mean, I don't know
Yeah.
whether you or others are aligned with this concept.
Yeah,
Please
that
check
But
is
I
out.
what it
don't
is.
think so. We should take the narrow range because then we are not covering the whole more range of data.
Hmm.
That's my understanding. Is
Okay.
it? So
So
you make it clear.
general practice is when you generate the confidence interval, the model automatically, the function automatically determines the confidence interval for the entire range. Okay, what is the general ideal way? Ideally, you will see 95% only. Okay, but the understanding is correct. So whether you choose lower range or higher range, it essentially does not matter. But what you are saying is, I am confident that my point lies closer to the mean. That means my value, in other words, if you are calculating, my point has lower error rate. Okay, if you're talking about RMSE confidence intervals, you are saying whatever the best fit line is, my point lies closer to the best fit line. Okay, I'm 95%, I have a confidence interval of 95%. That means my point lies within that range. Hence, it is closer to the mean. Okay, that is what it is. Doesn't, for now, just park the question whether to choose narrow range or higher range, because it also depends on the distribution, what type of distribution it is. Generally, we calculate for z score. Sorry, we calculate for standard deviations only, standard distributions only. But the challenge here is, okay, this could be a standard deviation, standard distribution. This could also be a standard distribution, right? And this could also be a standard deviation distribution. So if you notice, all the three distributions have the same mean. Now how will you choose the confidence interval? So for now, just park the question of narrow or broader range. Okay, for this, two standard deviation could be here, three standard deviation could be here, but for this one it is only here, right? Three standard deviation ends here only, two ends here, something like that, one ends here, something like that. So that's what. So for now, just park that question. We will look take it up in data analysis. Okay. For now, just understand what confidence interval is trying to tell you. Okay. So confidence interval is a measure of how far away your point lies away from the mean. Okay. So for this one, for example, this trial, the fifth value that you see, your entire range confidence interval of 0 to 95% is this length of the line, and that length of the line is not touching the mean, which means this is a bad prediction. Okay, here rest of them are good predictions, decent enough predictions, because the means of those points, central points, they are closer to the line, but here it is far away. So this is a bad prediction. So we can see that is what 95% of the times the blue line, or which is your sample mean, overlaps the red line, and 5% of the time it is expected to not overlap. Okay, that is by nature. Okay, 5% you will think that it may not be a good prediction. Have you understood the concept of confidence interval?
Yes.
Okay, so we can also look at how we are calculating. So if you want to mathematically see, understand, so if you take n greater than N value is just the number of data points. Don't worry about it. Size of the sample basically. So which goes to your denominator. Okay. So again, S is the standard deviation. Sigma is also the standard deviation. It's just that sigma is the standard deviation for sample, which 99.99% of the time which is what we deal with. We deal with sample data only. Here they have indicated S is the uh, same thing, standard deviation for population. Okay, so don't worry about this. Here they are considering if the number of samples increase 30, then we are kind of assuming it as a population, but generally don't worry about it, we only about this formula. Okay, so in this formula if you want to calculate, the question would be like, so for randomly selected 30 apples, okay, from a large population, okay, if you want to measure the diameter as the mean diameter, if it was 91 millimeters and standard deviation was 8 millimeter, can you calculate the 85% confidence limits? How, what would be the range of the means that will fall under 85% confidence mean? Very simple, we have the formula already. So x bar plus z into s by root of n. So you just substitute, z value is given. Okay, z value is 8 millimeter. Okay, 8 millimeter divided by okay, 1 second. So z value is 1.44. So this again you have to, I think, calculate separately, which they have not shown in this formula. uh, Z value for confidence level, where is the formula? Z of c. Okay, z score again you have to calculate using a different formula. Okay, so that is given by x minus mu by sigma. X is the actual value, mu is the mean value, sigma is the standard deviation. So uh, if you calculate this, you will get the z value. Again you have to substitute here. This they have not shown in this formula anyway. So this is mean. Okay, mean value is 91, standard deviation is given as 8. I have taken s. Z value you can calculate by substituting in that formula. N value is given. So once you get all these values, you are getting 85% of the time. Okay, you can say, okay, I think 85% confidence is multiplied with okay, what is 1.5 of 8? 1.5 times 8 is, okay, 1 second, calculate. I just wanna cross verify. 1.5 into, is 1.2, not 1.44. Okay. Anyway, so they have calculated the 85% confidence limit, and that turns out to be 91 plus or minus 1. After substituting, finally you will get plus or minus 2.1. That means there is a variation of 2.1 millimeters in the diameter of the apple. So
How
85%
have
of
we
the time. Mhm.
how do we calculate z value here 1.44 because they have given us can we just have the series once again 1.44 that
Yeah,
is calculated because they are given the standard deviation of 8 millimeter.
yeah,
So how
standard
that
deviation of 8 is given here, but
yes
z value they
and
have calculated separately, and which they have not shown here. Okay, so
yeah,
here you are taking
x
x minus mu by
minus
sigma.
mean upon standard deviation. Okay, fine, fine,
Okay, that
great.
they have resubstituted. Let's look at another example, better example. Maybe we'll get some hints here. A
Mhm.
random sample of 10 scores is taken. Okay, now you are being asked what is the 95% confidence limit for the mean of the whole sample. So mean is you are calculating 8. Okay, but because this is a sample, you have to use sample formula only. So for that you are calculating the s value. S value is, therefore s is 1 minus 1 by 9. Okay, just cross verify if they are substituting correctly. Into 1 by 6, okay, root of 4.42 for 95% confidence. Now you are multiplying. I want to check here something is, um, mathematically point 1. So how did they take the z value is what I want to know again. um, they have substituted in this formula, but how did they get the z? Here also they have used the z calculation separately, um, but mean is given, right? Mean is also not given, is it? Mean is given 8.
Yeah, it is
X,
calculated. X bar is calculated, sigma is calculated. I mean,
and
the
I want to
standard deviation is
know x
calculated.
value. X value
X
is
is the
zero point 0.9 of 8, or let's do the reverse calculation. You'll get to another z value. Z value is x minus x bar, but how did you get the x value is what I'm trying to understand here. X value should be 4.422 minus 8 by sigma. Sigma is how much given? um, Sigma is for 90%. I think you have to calculate even sigma for this particular thing. um,
sigma itself will be the standard deviation, right? S, that is 4.44. So we'll multiply 4.4221
then z
into,
is different here, no? That's what I'm.
no, let's multiply and do the reverse calculation.
Okay,
4.4221
so
into
4.422
1.645
into.
plus 8. So that is 15.27. So that is what X value. Now, how they got this X, I mean, where they got this X is a matter of concern for us.
Okay, anyway, we will look at better examples. Okay, here
No
they
worries.
have
No
not
worries.
clearly shown z value, but mathematically we just understand this is what the formula applies. Okay, here you have to also calculate z value separately, and once you calculate z value separately, this is what at the end of the day you can infer. You can say that my value of 91, whatever the mean you have taken, there is a 85% confidence interval that the mean differs by 2.1. Mean of the diameter of the apple differs by 2.1. 85% confidence interval, so that way you can infer it. But again, we will see the working example. Okay, so again, you don't worry about all these mathematics. So they have just taken a uh, normal distribution. For that they have calculated ppf, standard deviation. Okay, and all these functions are already readily available in stats model. Okay, if you do import stats model, you will get all this. They have taken um, the square root. But if you want to actually understand confidence interval, I think you can understand here only. First, intervals they have taken, sample mean, sample size they have taken. Okay, sample size is n value. Z critical is they have calculated the. Okay, so they have used a different calculation, like we understood. Z value they have calculated using some other methodology, which they are directly substituting. So here we have a direct function. You If you pass the quartile function, quartile value 97.5% confidence interval you want to, I mean 97.5 quartile value if you want to calculate, for you can pass it into this function. You get z critical, and then standard deviation is straightforward. And then you also have, if you are calculating for higher value 0.975, you also have to calculate for lower value 0.025. That also is calculated here. Now margin of error they have calculated. Basically confidence interval is nothing but mean plus margin of error. That's all confidence interval is. Now what is this margin of error? Margin of error is nothing but that z critical that they have calculated. If you can just check here, percent point function, okay, ppf. So inverse of cdf, cumulative distributive function, right, that we saw. It's a inverse of that. So it's just calculating. Okay, so we will have to dig deeper into this notes to understand what it is actually calculating, to understand z critical. Anyway, so once you calculate the z critical, then it becomes easy. You have to just divide this standard deviation divided by square root of sample size. Okay, once you do that, you will get margin of error. That margin of error, higher or lower margin of error, will give you the confidence interval. Okay, that is how they have shown this for 25 different trials. Now if you want to understand what is this stats.norm.ppf function, you can just check. So you have a complete manual for this. Okay, so you can go ahead and check what is that ppf function, percent point function, and also understand how it is calculating and all of that. Somewhere here if you notice, ppf is point percent function. If you go down, it will give you the, still want to check the accuracy of cdf ppf. Okay, this is pdf. Okay, not much here, maybe um, some other sources you have to understand how it is calculating. How proper to use this function, explain it to me. Yeah, someone had the same question. um, Okay, it takes a percentage and returns the standard deviation multiplier for what value the percentage occurs at. Okay, it's also equivalent to one tail test. Okay, so we will see what this one tail test is in hypothesis testing. There we will understand how this is calculating. But for now, maybe you can, what you can do is just understand whatever the confidence for whatever the limit you want to apply for confidence interval, you can pass it as a quartile value for ppf function. This takes the percentage value, and to that percentage value it does something called one tail test, and on a basis of standard deviation, it will do the mathematics and get you the value. Okay, z critical value. And that z critical value itself, that range, that itself can be multiplied with standard deviation and divided by square root of n to get the margin of error. Okay, so that is
For
how you get
Z
this.
critical,
Mhm,
okay, so for Z critical,
mhm.
we are not using the third quartile, right? Because it is 97.5, so
Honestly,
it
we
is
are not
almost the
using any
fourth
quartile
quartile.
here. What we are
Uh-huh.
trying to calculate here is, we want to know how many of those values lie within 97.5 confidence interval. So we have passed
Okay,
that quartile value.
okay, so we are passing that percentage of confidence interval as
Hmm,
the quartile value,
hmm.
and we are, so this is the upper end of
Limit.
that range, and the lower end of that range being the one fourth quartile.
Yes.
Point, no, it is 0.025.
Yeah.
Okay.
100 minus 1 minus 0.975 will give you this value.
Okay, got it, got it. Thanks.
Okay, 1 minus this value will give you this. So this is how they have taken calculated the confidence interval for 25 different trials. So if this is clear, then I think we can stop the class here. I will share you this list. Please go through the theory part also. Try to understand various concepts, because these are going to be heavily used concepts. This entire statistics is important. So next class we will see hypothesis testing, very very important. Okay, we will see what are parametric tests, we have non-parametric tests, and how to apply this comparison of p values, okay, for various tests, and thereby prove either you accept or not accept the null hypothesis. Okay, so, or alternate hypothesis in other words. So this way we will calculate the hypothesis testing, and we will also look at some comparative statistics, which is your nothing but your tests, various tests, when to use them, how to use them, and all of that we will see. And finally we'll be left with one final topic, A B testing. I can't tell you how important this is, extremely important. Okay, extensively used, honestly speaking. So you have to learn statistics very well for you to be a good data analyst or data scientist. Okay. um, yeah, not maybe not much for ml engineering, but definitely required for data analyst and data scientist. Okay, I will stop it here.